In 1970, I discovered that everything you've been taught about particles is wrong. Electrons, quarks, photons, they're not point-like objects, they're strings. One-dimensional filaments vibrating in space-time. I know how that sounds. When I first realized it, I thought I'd made a mistake, but the mathematics was undeniable, and it changed physics forever. Let me take you back to 1970. I was at Yeshiva University in New York, not exactly the center of the physics universe. I was working on the strong nuclear force, trying to understand how quarks are held together inside protons and neutrons. Nobody had a good theory for this. The strong force was a complete mystery. There was this mathematical formula that had just been discovered by an Italian physicist named Gabriele Veneziano. It was called the dual resonance model, and it did something remarkable. It described how particles scatter off each other in the strong interaction. The formula was beautiful, too beautiful. It worked better than it had any right to. I became obsessed with this formula. I'd sit in my office for hours, staring at the equations, trying to figure out what they meant. What physical picture did they correspond to? Because in physics, math isn't enough. You need a mental image. You need to be able to close your eyes and see what's happening. One afternoon, I remember this clearly. I was working through the mathematics of how this Veneziano amplitude behaves, and something clicked. The formula wasn't describing point particles bouncing off each other. It was describing something else entirely. It was describing the quantum vibrations of a string. I threw my pen down. That can't be right. Particles are points. Everyone knows that. You can't have a particle that's extended in space that violates everything we thought we knew about quantum field theory. But I kept checking the math, and it kept saying the same thing. The Veneziano amplitude is exactly what you'd get if particles were tiny, one-dimensional strings vibrating in space-time. Different vibration modes had different particles. An electron is one vibration pattern. A quark is another. A photon is yet another. I thought I was going crazy. I didn't tell anyone for weeks. I just kept working on it, trying to find the mistake. There had to be a mistake. Then I found out something that made me feel a little less crazy. Two other physicists had independently come to the exact same conclusion at the exact same time. Yoichiro Nambu at the University of Chicago and Holger Nielsen in Copenhagen. None of us knew about each other's work. We'd all looked at the same mathematics and seen strings. That's when I knew we were onto something real. When three physicists in three different countries all make the same mistake, it's probably not a mistake. All right, let me back up and explain the problem we were trying to solve. In the late 1960s, physicists had just discovered quarks, these fundamental particles that make up protons and neutrons. Murray Gell-Mann and George Zweig had proposed them a few years earlier, and experiments were starting to confirm they existed. But there was a huge mystery. Quarks are never seen alone. You can't pull a quark out of a proton. They're confined, locked inside, and nobody understood why. The force holding them together, the strong nuclear force, didn't behave like anything we'd seen before. In electromagnetism, if you pull two charged particles apart, the force between them gets weaker. It follows an inverse square law, but with quarks, the opposite happens. Pull them apart and the force gets stirran gr. It's like they're connected by a rubber band that gets stiffer the more you stretch it. This was completely baffling. How do you write down a theory for a force that behaves like that? Then Gabriele Veneziano came along with his dual resonance formula. It wasn't a complete theory, it was more like a mathematical guess, but it worked. It predicted the right scattering amplitudes for hadron collisions. The problem was nobody knew what it meant physically. The formula had this weird property called duality. In normal particle physics, you can think of a scattering process in two ways. You can think of particles exchanging other particles in this channel, or you can think of them exchanging particles in the T-channel. These are two different ways of drawing the same Feynman diagram. Usually you have to calculate both contributions and add them together. But Veneziano's formula automatically included both. It was dual. This channel and T-channel were the same thing from different perspectives. That's not how point particles work. So there I was staring at this formula, trying to figure out what kind of object would naturally have this duality property. And that's when it hit me. A string. If you have a string instead of a point particle, and you let it sweep out a two-dimensional surface in space-time, what we call a world sheet, then the S-channel and T-channel are just different ways of looking at the same surface. They're dual by geometry. Let me give you an analogy. Imagine you're looking at a piece of paper. You can measure its length and width, or you can rotate it and measure its width and length. It's the same rectangle, just described from two different angles. That's duality. For a string sweeping through space-time, this channel is like looking at the string from one angle, and the T-channel is like looking at it from another angle. They're the same process, just viewed differently. And here's the kicker: when you work out the quantum mechanics of a vibrating string, you get EXACTL, the Veneziano formula. Not approximately, exactly. The mathematics of a relativistic quantum string produces Veneziano's dual resonance amplitude as a natural consequence. I sat there in my office, stunned. This crazy idea that particles are strings actually worked. Okay, so let me explain how this string picture actually works, because it's not as simple as just saying particles are strings. There's a lot of depth here. First, we're not talking about strings like you'd find in a hardware store. These are quantum strings. They're one-dimensional objects with quantum mechanical properties. They have tension, they can vibrate, and they're incredibly small, about 10^35 meters long. That's the Planck length. A billion times smaller than an atomic nucleus. At normal energies, these strings look like points. You can't resolve their structure. That's why particle physics had worked so well up until then. We were looking at strings from so far away that they looked like dots. But when you do the full quantum mechanical calculation, the string nature becomes essential. Here's how it works. A quantum string has different modes of vibration, like a guitar string. A guitar string can vibrate at its fundamental frequency, or at harmonics, twice the frequency, 3 times the frequency, and so on. Each mode produces a different musical note. For a quantum string, each vibrational mode corresponds to a different particle. The lowest energy mode might be a graviton. The next mode up might be a photon. The next might be a quark, and so on. Different particles aren't different fundamental things. They're different vibration patterns of the same underlying string. This was mind-blowing to me. It meant that all the particles in nature, electrons, quarks, photons, neutrinos, everything, could be explained by a single object, a string. Different particles to different notes on the same string. Now, there was a problem. When I worked out the mathematics, the strings needed more than 4 dimensions to vibrate in. In fact, they needed 26 dimensions. 26! 4 dimensions we know about, 3 of space, 1 of time, plus 22 extra dimensions that we can't see. That sounded ridiculous. But here's the thing, maybe those extra dimensions are curled up so small that we can't detect them, like a garden hose. From far away, a hose looks one-dimensional, a line. But if you're an ant crawling on it, you realize it has a second dimension, the circular direction around the hose. The extra dimensions in string theory could be curled up like that, too small for us to see. This idea of hidden dimensions went back to work by Theodor Kaluza and Oskar Klein in the 1920s. They'd shown that if you add 1 extra dimension to Einstein's general relativity and curl it up, you get electromagnetism for free. It pops out of the geometry. So the idea of extra dimensions wasn't new. What was new was that string theory required them. You couldn't make the theory work in just 4 dimensions. The quantum mechanics of the string forced you to have more. I should mention the original string theory I discovered. The one that comes from the Veneziano amplitude is called bosonic string theory. It only describes bosons, particles like photons and gravitons. It doesn't describe fermions, particles like electrons and quarks. A few years later, other physicists figured out how to include fermions by adding supersymmetry to the theory. That's called superstring theory, and it only needs 10 dimensions instead of 26. But the basic idea is the same particles are vibration modes of strings. Now, here's where string theory gets really interesting for the strong force problem. Remember, I was trying to understand quark confinement, why quarks can't escape from protons. The string picture gave me an answer. When you have 2 quarks inside a proton, they're connected by a string, a color flux tube, we call it. The string is made of the gluon field, the field that mediates the strong force. As you try to pull the quarks apart, you stretch the string. The string has tension, like a rubber band. And because the string has constant tension, the force doesn't decrease with distance. It stays constant. Eventually, if you put enough energy into pulling the quarks apart, you don't separate them. Instead, the string snaps, and the energy goes into creating a new quark-antiquark pair at the breaking point. You end up with two mesons instead of free quarks. That's confinement. Quarks are tied together by strings, and you can't break the strings without creating more quarks. This was incredibly satisfying to me. The string idea didn't just explain the Veneziano amplitude, it explained why quarks are confined. It gave a physical mechanism. I wrote up my results and published them in Physical Review D in 1970. The paper was called Structure of Hadrons Implied by Duality. That was my string theory paper, the moment I put strings into fundamental physics. At the time, I thought this was just a model for the strong force. I had no idea that strings would eventually become a candidate for a theory of everything, a theory that unifies gravity with quantum mechanics. That development came later in the mid-1970s when people realized that string theory automatically includes gravity. It has a vibration mode that behaves exactly like a graviton. But in 1970, I was just a young physicist trying to understand the strong force, and I'd stumbled onto something that would consume the rest of my career. When I first published this work, the reaction was mixed. Some physicists got excited. They saw the potential. Yoichiro Nambu, in particular, was developing the idea independently, and his work was more mathematically rigorous than mine. Holger Nielsen in Copenhagen was also working on it. The three of us are considered the co-discoverers of string theory, but a lot of physicists were skeptical. Strings? 26 dimensions. It sounded like science fiction, and to be honest, the theory had serious problems in those early days. The spectrum of particles included a tachyon, a particle with imaginary mass that travels faster than light. That's unphysical. It meant the vacuum state of the theory was unstable. We didn't know how to fix that. Also, the theory was incredibly hard to calculate with. Unlike point-particle theories, where you have nice Feynman diagrams and well-defined perturbation theory, string theory was a mess. The mathematics was unfamiliar. People didn't know how to extract predictions. So for a few years, string theory was this niche topic. A small community of us kept working on it, but most physicists ignored it. Then, in the mid-1970s, something happened that changed everything. Quantum chromodynamics, QCD, was developed. This was the proper quantum field theory of the strong force based on quarks and gluons. It explained quark confinement without needing strings. The strings I discovered weren't fundamental strings, they were effective strings, emergent objects made of gluon fields. At that point, a lot of people thought string theory was dead. If QCD explains the strong force, who needs strings? But then John Schwarz and Joel Shirk realized something incredible. They noticed that string theory has a massless spin-2 particle in its spectrum. That's a graviton. String theory automatically includes gravity. This changed the whole game. String theory wasn't just a theory of the strong force. It was a theory of quantum gravity, the thing Einstein had spent the last 30 years of his life trying to find. Suddenly, string theory went from being a failed model of hadrons to being a potential theory of everything. I remember hearing about this and thinking, holy shit. We've been working on this obscure model of mesons, and it turns out to contain the key to unifying all the forces of nature. Through the late 1970s and early 1980s, a small group of us kept working on string theory. Michael Green and John Schwarz made huge progress on the mathematics. They figured out how to cancel anomalies, quantum inconsistencies that plague most attempts at quantum gravity. Then, in 1984, came what we call the first superstring revolution. Green and Schwarz showed that superstring theory is anomaly-free in exactly 10 dimensions. This was a huge breakthrough. It meant string theory could be a consistent quantum theory of gravity. Ade Witten got involved. David Gross got involved. Suddenly, every brilliant young physicist wanted to work on strings. I was at Stanford by then, and I dove back into string theory full time. The next decade was one of the most exciting periods of my career. We discovered D-branes. We found dualities between different string theories. We realized that all 5 superstring theories are different limits of a single 11-dimensional theory called M theory. And through all of this, I kept coming back to that moment in 1970 when I first realized particles are strings. It's funny how one insight can shape your entire career. String theory today is a mature research program with thousands of physicists working on it worldwide. We've learned an enormous amount. We know that strings aren't just one-dimensional objects. They can end on higher dimensional objects called D-branes. We know that the theory has deep connections to black hole physics through the holographic principle, which I'll talk about in another video. We've also discovered that string theory predicts a vast landscape of possible universes, about 10,500 different vacuum states, each corresponding to a different way of curling up the extra dimensions. This is called the string theory landscape, and it's one of the most controversial ideas in modern physics. I've spent a lot of time thinking about this, and I'll explain it in a future video. But there's still a lot we don't understand. We don't have a complete formulation of string theory. We have perturbative string theory, a way of calculating when strings are weakly interacting, but we don't have the full non-perturbative definition. We don't know what the theory is at a fundamental level. We also don't know how to connect string theory to the real world in a unique way. There are too many possibilities. How do you pick out the vacuum state that corresponds to our universe? That's an open question. And we still haven't made a testable prediction that could be verified in a laboratory. String theory operates at energy scales far beyond what we can reach with particle accelerators. The strings are too small to see directly. Some people criticize string theory for this. They say it's not really physics if you can't test it. Lee Smolin, a good friend of mine, has been particularly vocal about this. He thinks string theory has become mathematical philosophy rather than science. I disagree. I think string theory is the best idea we have for quantum gravity. And I think the indirect evidence, the way it solves problems in black hole physics, the way it unifies forces, the mathematical consistency of the theory is compelling. But I admit, we don't have the final answer yet. String theory is still a work in progress. These days, my students and I are working on applications of string theory to other areas of physics. We use the ADESC CFT correspondence, a duality discovered by Joan Maldacena, to study quantum chromodynamics and condensed matter systems. We study black holes using string theory techniques. We explore quantum complexity and how it connects to space-time geometry. All of this traces back to that original insight in 1978, particles or strings. It's been 56 years since I first realized this. I'm 86 years old now. I don't know if I'll live to see string theory fully developed and tested, but I'm still working on it every day, still teaching it to graduate students, still trying to figure out the next piece of the puzzle. Because here's the thing, even if string theory turns out to be wrong, even if nature isn't actually made of strings, the mathematics we've discovered is too beautiful, too rich to be an accident. It's telling us something deep about the structure of reality, and I want to know what that is before my time is up. You know what I find remarkable? The idea that particles or strings came from pure mathematics. I wasn't trying to revolutionize physics. I was just trying to understand a formula, the Veneziano amplitude, and the mathematics led me to strings. That's how physics often works. You follow the math wherever it goes, even if it takes you somewhere strange. And if the math is beautiful enough, if it's consistent enough, if it solves real problems, then you trust it. Strings in 26 dimensions sounded crazy in 1970. It still sounds crazy, but the mathematics works. And over the past 50 years, string theory has solved problem after problem, from quark confinement to black hole entropy to the unification of forces. I don't know if particles are really strings. I won't know for sure in my lifetime. But I know this thinking of them as strings has taught us more about the universe than any other idea in the past half-century. And that's good enough for me. My father wanted me to be a plumber. He used to say, "You ain't going to be no engineer. You're going to be Einstein." Well, I didn't become Einstein, but I did become a theoretical physicist who discovered that the universe is made of strings vibrating in 26 dimensions. I think my father would have gotten a kick out of that. After all these years, the universe still surprises me, and that's why I keep doing this. That's why I wake up every morning and think about quantum gravity and string theory and black holes. Because there's always one more surprise waiting, one more insight hidden in the mathematics. And I'll be damned if I stop looking for it now.